Okay, so welcome everybody. As the top part of the slide says, my name is Steve, and as that middle part of the slide says, I'm a bit of a geek. Now, if we've all joined the right session, this is about retro computing and how to build a game for an old computer, specifically how I built an old game called ZX Adventure. Not a plug, because you can just download it from internets anyway, but it did, spoiler alert, it did come out as a proper cassette. So I'll cover that over the course of the next half an hour or so and show you how I actually got there. But before then, what is it we're going to be going through? Well, I'll start off about why I did this. What drove me to do something fundamentally so out of date? I'll look at the building process, the tools that I used, the methodologies that I used. I'll also go into some of the technical details about the spectrum and the mechanics of what I had to do to work with that architecture. Although most of us probably know a lot more about this than I do, I'm the one with the screen. So I will be telling as best I can how it works. I'll then look at how I built the game element itself and how I play tested the game, and then looking at the collateral, which is all the other bits of stuff that have to go around the project to turn it from just a piece of code to an actual game. So with all that in mind, we'll start at the beginning with who am I? What have I done to deserve a place on this video screen? Or as this slide should probably be called, the ego slide. That's where the speaker brags about themselves for 10 minutes and everyone else wishes this was a pre-recorded session and they could just fast forward through this bit, but you can't. So I'm a developer. I've always been a developer. I started off as a junior developer writing things for Windows PCs. I worked through to be senior developers. I've done CTO things, and I've done this in a lot of different domain spaces. So I've done this in education technology. I've done this for serverless. I've done this for games as well. I'm also a big fan of the open source world. I've spoken at conferences on this. I keynoted FOSDEM last year. I've spoken about new technologies, things Alexa, although it's not new now, it was when I started. And there's a lot of different things, but it's always about me developing something for a platform. But essentially, none of that's important. Everything that's on that slide right now is not important. What's important is what isn't on that slide. This is a game for the ZX Spectrum, for the ZX81 as well. They both use a Z80 processor. I am not a professional Z80 programmer. Also, this is an old machine, so it would make sense that I would be working at a university or a museum, studying and preserving these old computers. I'm not. I help out at the Computer Museum in Cambridge a bit when it's open, but otherwise, I'm not a professional historian of computers, which is a very, very long-winded way of saying, this is not my day job. This means I'm doing this for fun, which means if I can do it, anybody can do it. Everything I'm going to show and share here, I've learned through doing, I've learned through things online, things that I've learned, bits that I remember from the dim and distant past. So with that in mind, we should actually ask that big question, well, if you're not paid to do it, if you're just doing it for fun, well, why? What is the whole origin story, as it were? So the origin goes back to 2015. I was spending a rather enjoyable evening just watching videos and documentaries on old computers. I can't remember how many I watched, probably 3 or 4 over the course of the evening. And it was amusing. It brought back some memories. It was interesting to see how other people saw the industry from their side. And it got me thinking on how nobody builds retro games anymore. Not really. There's not many people that do it. A lot of people are building very modern games using retro visuals. They will use all the computing power that exists, and they'll use it to render 4 red and green blocks. They're not using the old technology in the old ways. They're not limited to 40 kilobytes of memory. They're using gigabytes of memory and gigabytes of like the current flow of the engines. So things like Unreal or Unity engines, massive piece of technology to render something that was done in 1982 in 40K. And I thought, it would be good for me to go back and just remind myself how easy and or difficult it was to write games in that era. So I started off, I looked around and said, right, well, how do I do it? And that is something we'll come to shortly. If I want to build a game, I suppose one should ask, what game? And this is where I thought I'd have an advantage. As I mentioned earlier, I used to work in games. I ran a couple of game studios. I built games for various platforms, Windows platforms. I built stuff for PlayStation, Xbox, GameCube, as well as online games. And as a consequence, as every game developer will tell you, they have a very large number of notebooks, lots and lots of pages in each, all filled with games ideas. Games ideas they'll probably never get to do, but we just keep that journal anyway. It's one of those things where if someone comes up and says, oh, I've got a fantastic game you should make, I'm the ideas person, you should just make this game. It's like, we don't need them. Every game developer has more game ideas than they'll ever use. And I had notebooks full of them. So I thought I could build a game from any one of these notebooks. I've got 1,000 game ideas. I could build any one of them. And then I decided that I wouldn't. I was being quite method in my performance here. If you ever hear an actor talking about their workflow and their ethic, they go, well, what's my motivation here, darling? That's a very actor type approach. And I was going to follow exactly the same. So I said, if I was writing a game for the Spectrum in, say, 1982, how would I go about it? And I reasoned that in 1982, you wouldn't invent a brand new game concept a lot of the time. What you would do is you would find an existing game that didn't exist on your platform and you'd copy it. Sorry, you wouldn't copy it. You would be inspired by it. You would take those ideas and that type of gameplay mechanic, you might change some graphics, and then you'd ship it out under a different title. Sometimes you wouldn't even ship it out under a different title. There were a number of games in the early 80s that were called Star Trek, because it took a little while for Paramount Pictures to realize people were using their intellectual property without paying. So they all got changed to Space Trek or Dragon Trek or some other named title. But essentially every game started off as a copy of something else. Even the very famous games of the era like Manic Miner and Jet Set Willy. Manic Miner started off as a copy of Miner 2049, I think. So you can see there's an obvious lineage there of old games, of previous existing games, of arcade games being modified for the home computer market. So I figured that's what I would do. I would take an existing game and I would mess around with it a bit and produce my game. I was more interested about the mechanics of programming a ZX Spectrum back in the day than I was interested about creating a brand new original game title. And the game I picked was Adventure by a guy called Warren Robinett. And this is a fairly traditional game. It was on the Atari 2600, and you moved through various rooms. You would pick up swords. The swords would kill dragons. That when the dragon was dead, you could pass the dragon safely to collect treasure. You'd return the treasure home, and you'd score points. It's not a rocket science game, but it was a very fun game for the time, and still holds up fairly well today, considering. So I figured that would be a nice type of game which I could adapt for the Spectrum. But as I say, I was wanting to build a game. I wasn't particularly interested in the engine. I have built a lot of engines in my time. My role as a professional games developer, I spent more time building the engines and the tools for the game than I ever did building the game itself. So I wanted to focus a lot of my creative energies and my time on the game itself, even though it's simple. Also, I wanted to consider how I should build the game. Now, even back in the 80s, games would be built in one of two ways. You'd either build it natively, so you would load an assembler into your machine, such as the ZX Spectrum, and I still have mine here. It almost works. And you would load an assembler onto the machine. Sinclair produced an assembler called Zeus, and Highsoft produced Gens 3. You'd load that code into the machine. That would have its own editor. You would type in your code. You would save it as plain text out onto tape. Yes, tape, remember? Yes. And you would then assemble that into a binary, also onto tape, which you could then run and debug on the machine. That's quite a lot of hard work, especially nowadays. And even people back in the 80s often wouldn't do this. The aforementioned Matthew Smith of Jet Set Willie and Manic Minify, he didn't do that. He did talk about programming on the rubber key spectrum, but what he really did is he did cross-platform development, which is to say he would have a CP/M machine. I think he had actually a Tandy something or other at the time when he started. And this bigger machine would do all the assembling, which was slightly faster than the Spectrum would do it. It would generate a binary. It would squirt the binary down a serial cable to the Spectrum, where he could then play and test it. This has the fairly obvious advantages if your game has a bug and it crashes the machine. You don't have to reload the assembler into memory because it's already on the other machine. And so looking at these two approaches, it was fairly obvious that I was going to go with the cross-platform approach. I could edit the code in my nice fancy Sublime editor with mouse control and everything else I didn't have back at the time, and build my game that way. Next up was a case of saying, well, what else do I need? So obviously for cross-platform development, I'm going to need the editor and I'm going to need some kind of assembly tools. I decided I was going to do it in Z80. There are C compilers that will generate suitable code. Unfortunately, C code is too big in the most part for these old machines. You can build code, you can build games for them, but you have to build fairly small games, because even at this level, as in a 48K machine, even if the C code is really well optimized and it's only twice as large as the assembler would be, it stands to reason your game can only be half the size. Your game code, that is, your assets are always going to be a fixed size. So with that in mind, I've got my text editor. I'll get some assembler tools, and then I need to say, well, I need to run it, and that would be, for example, on an emulator. But the assembler was not the first thing I looked for, nor was the emulator the first thing I looked for. The first thing I looked for was sample code. I wanted something that I could just run. I could just assemble this, put it on an emulator, and see how it worked. I'm not one for necessarily reinventing the wheel, even though I can. I've proven to myself before I can reinvent the wheel if I want to. It doesn't hold as much drive as it once did. And because I know people have built Spectrum games before, and I know people are still building Spectrum games in a fairly small number, I knew there'd be some sample code out there on the interwebs. So I went out, I looked for some sample code for ZX81 and for Spectrum, and I downloaded it to build on my machine. Now, I should probably point this out sort of fairly early on. I will probably accidentally or intentionally use the phrase ZX Spectrum and ZX81 often interchangeably. This is because the process of building this game has gone through several different phases. Back in 2015, when I was looking at the idea of, well, I could build a game for the Spectrum, I went ahead and built a game for the Spectrum. I built ZX Adventure. This is what we're talking about. But and after I built ZX Adventure for the Spectrum, it got picked up by the people who built the ZX Vega. And they included it in the hardware on the very first and subsequent releases of the Vega. Once that had been done, I then changed it to be a ZX81 version. After all, they have the same chip, it uses the same language, it's a little bit simpler because there's no color, there's no sound, and no high resolution graphics in the version I was going to write. So I figured I'll do a ZX81 version, and I did. And I ported the ZX Spectrum version across to the ZX81. Then after I did that, I added a lot of things into the ZX81 game that I quite liked. So I then ported it all back to ZX Spectrum again. So over the course of the last 6 years, it's either been Spectrum time or ZX81 time or back to Spectrum. So even in my own head, I sometimes get confused as to which version I was ever working on. So this is one of the other reasons why I have both this is the ZX81 template code I use to guide me, and this is the Spectrum code that I use to guide me. So moving on from that, I have my sample code, I have my cross assembler, and I can use that assembler to build something that will load into an emulator, either a .p file or a .tzx file, and it will also generate a map file. Now, this map file is exactly the same type of map file you'd find in your C compiler or even in your obfuscated JavaScript file, which is to say, it's a big list in text that says, this function name is stored at this memory location. This variable is stored at this memory location. And as a consequence, when you're working through the binary, it becomes possible to see what data is in the memory. So when you're trying to track down bugs, you can see, oh yeah, this value keeps changing. That's the score, and you can go directly to it. The important part on the assembler, though, is that my sample code would build first time. Even though every assembler has very common mnemonics, LDA and RET for return, for example, they're all the same because those are the Z80 approved terms from Zilog. The assembler makers themselves would often have slight variations. And I'm jumping ahead of myself here, apologies for that. But some assemblers would use the semicolon to indicate comment. Other assemblers would use the hash to indicate comment. And I wanted to avoid that confusion. So I found the source code and then found an assembler which would just work with that source code. The other things I needed was an emulator, and it had to support the file formats which my assembler would generate, and it had to have a debugger. Now, over the course of the project, I used 3 different emulators because the type of debugger I needed at each stage differed, and we'll come on to what those were shortly. The other set of tools I needed were data converters. Now, although the amount of graphics used in the game are not excessive, and if you are able to see the back of the cassette, you can see it's just black blobs. Not really complex graphics, but still I needed a simple way of getting them into the machine. I didn't fancy typing in 768 hexadecimal numbers to get a screen display. I wanted to draw it in GIMP. I wanted to load it into a converter program that would then spit out the appropriate binary data. And these are some of the data converters which I found to be useful. Some are good for the ZX Spectrum, some were more useful for the ZX81. And I also, through a very small amount of code, wrote my own, which helped improve the process a little bit. Because the turnaround, although not long, is something that I try to minimize. In the day, if you have to wait 4 minutes for a game to load, you accept it because you know no better. These days, I know if I'm working on JavaScript, for example, I can hit F5 or Command R on my page will refresh, and all the changes that I've made suddenly appear instantly. That's the sort of turnaround that I've got used to. So whenever I have a development flow which doesn't adhere to that, it to me feels very sluggish. So I also had to build and modify some of my existing tools that would generate the code a lot more simply, which also meant sometimes it would be very specific to the project, and I could hack the code to write the destination file into my source directory directly, rather than having to download it somewhere, then copy it, then rebuild it. I could do that automatically. So with that in mind, what assembler did I end up using? As I've already said, it's whichever one would build the sample code I found online, and the assembler I found was Pasmo. I have no affiliation with Pasmo. I happen to use it because it built the sample code, and it seems to be fairly well, liked. There's a number of people out there that seem to be using it, so not just me. My considerations, as I mentioned, were that it would take that source code, so hashes and semicolons could be used interchangeably for comments sometimes. Do labels need colons? That can be confusing, particularly if you have a label that matches an existing opcode. Does it get translated as an opcode or not? Do you need a tab or some other form of white space before it gets treated as not a label? Every assembler creator had their own ideas on what should be valid. And also, how do you specify binary data inside source code? Now, all of this stuff, it's very easy to run, by the way, you just do that. But all of this stuff was important for me because I'd not used Pasmo before. When I was growing up, I would have to hand assemble all of my machine code. This was not because I'm a masochist, it's because my family and I could not afford to buy an assembler such as Sinclair Zeus. Yes, buy. Do you remember this when we had to buy software that does? Yeah, that seems like a very long time ago. That really kind of dates me now. So I would have had to have bought a physical cassette for assembler and couldn't afford it. So I ended up doing a lot of hand assembly myself. Obviously, wasn't going to do that anymore. So the spoiler of all of that is I have no preconceived ideas on what the assembler would do or its key shortcuts. And with that, here we have a small mid-lecture activity, which involves this. Nothing to do with Sinclair, nothing to do with the Spectrum, but it is about programming. And for those that can remember it, AM stands for Amiga and OS is operating system, which is a really bad name because it's basically just basic. And this box, massive box, complete with its price tag, 50 quid for this, is a version of BASIC which I used on the Amiga 20 years ago. Well, why am I showing this? Well, a while back, I had this idea for a project I called Ada 99. I was going to rewrite the very first computer program that Ada Lovelace created, and I was going to write it in 99 different programming languages. And one of the programming languages I decided to use was this Amiga BASIC. You know, I have it on emulator now, so I ran it up on the emulator, I loaded it up, and instantly I typed in the program. I remembered all the key shortcuts. I knew how to test the program, debug the program. I knew how to bring up the console. I knew the commands. I knew the very specific nuances of this version of BASIC. I'd not used it for 20 years, but I could still remember through muscle memory all the key shortcuts that I would use originally. I remembered the programming language, all the oddities in it, how to load, save, bring in banks, bring in extra pieces of it. And it's like, why? What part of my memory is storing this information? It has no use. It's just something in there that is now lodged forever. Key shortcuts for this software, and probably key shortcuts for a lot of other software as well. Which means if I was going back to an assembler, for example, that I'd used previously, but the key shortcuts were different, it means I would be perpetually hitting the wrong key shortcut because muscle memory would keep telling me, here's your key shortcut for build. Oh no, it's not on this assembler, it's over there. So because I didn't have those preconceptions, I managed to build the software without getting frustrated by bad key shortcuts or variant key shortcuts. So as a consequence, I didn't go stir crazy in doing this, which is a good thing. So back to the normal bits. So having now got an assembler, built my sample code into something, loading the data, and the first one, this just happened to be one I found. I can't say there was any particular reasoning behind it. I went to my directory of emulators, I clicked, it loaded the things in, I started going. Now, it's not a bad emulator per se, but it is a bit slow when it comes to importing files, which is to say I've built my assembler and it loads it in almost real time, which, as I've said, is not something that appeals to me. But it got me started, and it enabled me to take those original core routines, run them in the emulator, and debug them. And the debugger was decent, so I could debug the very basic core routines in the emulator to get myself moving. I also found that it wasn't GPL, which as an open source geek is a bit of a no-no some of the time. I hadn't realized it was not GPL when I started because I accidentally seemed to have found some source code to it once upon a time and it was in a directory, and I mistakenly believed, well, if I have the source code, it must be open source, therefore it's a good thing to use. But it didn't matter, it worked and it's still a decent piece of software, nothing against it. But from that, I went on to Zisa UX, and I hope I'm pronouncing that right. No one's corrected me yet. And this was my second emulator. This is properly OpenGPL, And this was very good for the hard to find bugs because this emulator contained a transaction log, which is to say every single instruction that gets executed, it writes a line to a text file. Program counter updates, gets changed in the text file. Register changes value, gets changed. So everything and the assembly instruction that it's executing at the time is listed in there as well. This is really good for those hard to track bugs where you've got to go through the loop 100 or 200 times before you spot something going wrong. You can just dump it out into the text file. You can say, well, I know it's gone wrong at this point. Where does A go to 0? Or where does my program counter jump off into the middle of nowhere? So it was very good for that. And a lot of this early engine work where I'd say, well, I've got my basic sample code. I've now manipulated it into something that I'm happy to work with an API that I think is good. All of that debugging was done in CSI-UX. And the GitHub link on screen is for anyone who wants to download it and have a play themselves. The third and final emulator I used was EMF Spectrum. Disclaimer, I wrote this one, so naturally it was going to become useful at some point in the development process. And for me, I used it for debugging the gameplay. Now, debuggers are quite hard to write anyway, because you're never quite sure what type of things everyone else is going to need for their specific case. Obviously, everyone needs to be able to change the register or to change the program counter or rewrite bytes in memory. But everything else is pretty much open for debate. What sort of things do you have on your breakpoint, for example? Fire this breakpoint when you've hit this program counter 20 times. But you might also want only fire on this breakpoint if it's hit this routine 20 times and the register is equal to 4,000, because that's the object that causes the bug. So you often need a lot of control in a debugger that a general purpose debugger doesn't give you. My EMF emulator is written in JavaScript, which, because it's in JavaScript and runs in the browser, you can not only use the emulator's debugger, but you can also use the JavaScript debugger as part of your debugging process. So by using that, I can add, by almost literally embedding eval JavaScript statements into my emulated code that lets me debug the gameplay very, very simply. And that came in very handy, because then I didn't need to reload my emulator or my assembled code into the emulator repeatedly. I could load it once. I can go, all right, yes, I can change that. It's running too fast. I change the number 8 to the number 6, and that's good. I don't need to reload it. I'll change the number in the source code and go on to the next thing I don't like. Oh, this graphic is animating too quickly. Okay, change the number directly by fiddling the JavaScript, and hey presto, it all works. And that emulator is on the Emulate site, if anyone wants to try that. I am quite lazy sometimes, and I haven't written an importer for the TZX format yet. So I had to load it into another emulator, export it as a snapshot, and then load it in. I'll get around to it one day. It's on the to-do list. So with that in mind, we should probably go on to what these core routines were all about. I keep saying I downloaded some sample code and then I changed it so it was a set of core engine routines that I was happy with. So what are they? Well, essentially, it was the sample code with some modifications. So I'd bring in the sample code, I'd test the assembly. So can I remember how to do a loop, for example? And I'd write the loop and I'd go into the debugger. It's like, okay, I'm getting the hang of the debugger. I understand how that works. I can still remember how to clear the screen, for example. I would test progress by changing the border color. This is a thing for the ZX Spectrum, not the ZX81, where I figured that I could just change the border color as I hit certain points in my code. This way I could see what it was doing, and if it got stuck in an infinite loop, then the border color would tell me where it got stuck without me having to forcibly break into the program to look at something. And I always quite like the idea of being able to non-intrusively debug a program, particularly as in some cases you might find bugs that only manifest themselves when they're running at full speed. Things like interrupts, for example, really mess you up. So what are these 3 routines? Well, my philosophy is that you only ever need 3 different routines to write an entire game. No matter how big the game is, if you're building this type of game, you just need 3 routines. You need one routine that draws a pixel. At X, Y on the screen, and in this color, draw a dot. That's all you need. You need a routine that will handle the input. Now, in this case, it's a keyboard, but it could also have been a joystick. And you also need some way of playing a sound. If you've got these three things, you can do everything. You want to clear the screen? Fine. Draw 7,068 dots in this color all the way across your screen. It might be slow, but you can optimize it later. You want to draw a graphic character? Fine. Draw 42 dots here, 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 and here. Again, it might be slow and there might be better ways of doing it, but it gets you moving quicker at the beginning as far as development time goes. And you'll then optimize later and find better routines. And you'll say, well, I want to draw an 8x8 graphic character. You'll then write a specific routine for that when you find you need it. I have a philosophy on, it's very easy to write a game that runs at 60 frames a second. If you play console games and you find them going slow and you exasperate at the programmers thinking, why can't you write a game that runs fast? It's like, well, we can. It's very easy. And the way to do it is you write a game that runs at 60 frames a second, and then you stop whenever that game drops below 60 frames a second. And then you optimize until it's over 60, and then you carry on. This way, the game never runs below 60, and you're only optimizing the code you need to. That's been my approach. And I did the same here. Unfortunately, I found very early on, because of the limited resources of that machine, the Spectrum needed optimized routines for drawing characters and clearing the screen almost immediately. But I didn't need to do that much work. And again, the source code is in GitHub if you want to have a look at how much work was needed to optimize those specific routines. Same with reading the input. If I can determine if any key is down, I can do everything else. And a symphony is just a lot of sounds played together. So I'll now drop into what potentially is more technical part of the talk, where I'm going to talk specifically about the hardware of the Spectrum. As I said, I'm probably not even the most talented Spectrum person here. So for those of you that are the more talented Spectrum programmer, please pipe up and yell if I'm getting something a bit wrong. I'm going through what has worked for me in the past. So the Spectrum itself, we know, created by Clive Sinclair and his band over here in Cambridge, and had a Z80 processor inside to do all the nice fun stuff, had color graphics, it had sound, and it had a dead flesh rubbery keyboard, which is still iconic even to this day. So this is an exploded view on the right. And I'm going to go through each of the sections in reverse order from what I just did. My hope is being that by taking it in reverse order, I get through the simpler bits first. And by the time we get to the end, we're on the much more complex, this is where you have to pay attention bit. So let's zoom in on that picture and let's look at sound. And this is the sound. It sits here on the bottom right of the board. And if you look at the diagrams for this, for either the circuit diagrams or the schematics, you'll see it's labeled as loudspeaker. Loudspeaker. Two things that do not apply to that unit on the motherboard. That is not a loudspeaker, that's a piezoelectric buzzer. It is not loud and it is not a speaker. It has two modes. It has on and off, in and out, nothing in between. So you can't even get volume the normal way of sending a different voltage across, or sending a different current through, I suppose I should say. I'm aware of the company I keep, so I should be probably more precise in my language. So all you can do is make this piezo go in and out. And the ROM provides a routine where you feed it a pitch and a duration, and it will make a buzzy noise for you. And if you don't want to use the ROM routines, that you like doing it the hard way, then that piezoelectrode sits on the output of 254. So whenever you use the out instruction in assembler, that's the piezo that responds. So if you look at the code, I don't know how many musicians we have with us tonight, but pitch 297, yeah, that could be a reasonable frequency, I guess. And duration 208, well, not quite sure what that means, probably milliseconds. So it does have some kind of reality, but that's not musical. The notes that come out of that are not really what they say. You have to compute these numbers via some mathematics, and these are the mathematics. This is what you'll find if you read the ROM code for the spectrum. You have to look at the frequency of the note and its duration in seconds. You then need to convert these into T states, which is the number of time states that the processor goes through. And you perform and you've got to bear in mind that because it's the processor that's going through each of these states, how fast is that processor being clocked? The spectrum was being clocked at 3.5 megahertz. So that magic number appears in these set of equations. Now, that's quite a lot of work to do. There's 4 steps there. There's nothing too difficult. A few divides, some subtractions, a multiply here and there. So there's nothing you can't do in 20 lines of code, for example. But there is no way you're going to write 20 lines of code for every time you want to make a beeping noise. There's no way you want the processor to be running 20 lines of code, because by the time you've done that, it's too late for the beep to sound. So what can you do instead? Well, you do what any self-respecting programmer will do. They'll optimize and they'll generate a table. So generated a table which indicates the pitch of the note in real world. These numbers on the left, 16, 17, 18, so forth, these are the MIDI note values for a particular note, C, C sharp, D, and so forth. And on the right is the magic number that you need to put into the beep routine to actually play that sound. There is then some modification of that number to get the duration to be the right value. And that means that I can compose a tune by just saying note C, crotchet, note D, crotchet, and so forth. Because these numbers map to that table. The duration then just divides the time down by shifting the numbers to the right and then calling that beeper routine. A lot of work for something as simple as just playing a rather dull monophonic melody line, but it was all I was prepared to do. At the beginning of the Spectrum's life cycle, that is pretty much what everyone did. But soon, with games that needed to have sound at the same time as doing animated graphics, so people had to write their own sound code by sending an out instruction, animating the graphic, sending another out instruction, animating the graphic, and so forth. Again, that was more work than I was prepared to do for this, so I didn't do it. There are 2 other sounds that appear in the game. There is a sweep sound, which just goes through all pitches from, I think it's 100 hertz to 1000 hertz or 2000 hertz. And I just repeatedly call the play sound routine for a very short duration. And there was a bang noisy effect, which I found online and put that in because I figured why not. And that is essentially sound. It is very, very simple because the hardware was simple. There's not a lot more you can do without really putting some effort in. And I didn't think it worth it for this particular project. Next, we have the keyboard. And this, to some of you, will explain everything you need to know about how the keyboard works. For mere mortals like myself, I need to work through it. Now, the keyboard on the Spectrum worked in the same way as the Jupiter Ace, perhaps unsurprisingly, and the Dragon 32, and a lot of the machines of that era, at least the ones I've written emulators for, all work on pretty much this same principle, which is of a matrix. So on the top, we have a series of address buses. They come down, so you will write something on the address bus by using, say, the out command, for example, and that will set up one or more of those lines. Then if a key is pressed, then that will take one of these data lines low. So you would feed in, for example, address here and check for data here. And if you got a data out when this address line went low, then that was the key pressed. If this data line went low, that was the key pressed. So to determine a single key being pressed, you just send the right number. There's a magic number that you send that says, look at everything in this column. And then you read out everything on the row to work out which of those buttons was pressed, which does mean you need to make, for example, in this case, 8 requests on each address line, and then check the bits of each of those 5 bits to work out if those keys have been pressed. But realistically speaking, you don't need to do that. You're only interested in a few keys. And if you've ever seen games where they say, you can press any of these 6 keys, they all move your character up, then this is why. They decided that we'll just put everything on the one line. So on this case, for example, line A14, if I take line A14 down to ground by using the appropriate out command, then I can check for the H key, the J key, the K key, and the L key, all with one instruction. That's quite a saving. So it was very common for that to be done. If you use VI, you'll probably notice that those keys are not dissimilar to the cursor control keys, because that's what the cursor control keys were on the old terminals. So they only needed one instruction to read 4 different keys. But enough theory, let's look at the practical example. So here is the practical example from the code. It's the code that waits for the space key to be pressed. This happens at the beginning of the game. And for that, we have A15, the most significant bit. So we load in that address, which is 7FFE, and we send that off to the out instruction, which goes on to the input-output bus, and that gets picked up by the keyboard. Now, A15 is 0. That's because the 7 is there. So it sends everything in that column down to 0. Now, if the space is being pressed, then that space will send that 0 through to data 0, which I do here by reading that keyboard in. I know I've said out earlier, it's the I/O system. It's actually sending things out, but it actually causes data to be read in. That I don't know why it works that way. It just does. It's hardware things. So you bring in that value, that data value, D0, D1, D2, D4, and so on. Gets the state of all of those buttons on A15. So you get the state of the space, the symbol shift, the M and the N and the B. It says, well, we're only interested in space. So we check to see if bit 0 has been cleared. And if it hasn't, then we say, well, let's go back and wait until it has. And that's what allows us to wait for the space key. To use a secondary example, here on the top right, the previous example was that 32766 example. The next one, if we were to do load BC 65278, that's the hex for FEFE, which is 11111110. That means A08. This means A8 is 0. I should have really chosen a different one there to, make saying this so much easier. But the A8 will go down to 0. That means it will check for every key of the V, C, X, Z, and cap shift. And then we can read off, sort of, say, if we want to know if V has been checked, we can do a bit 4, and that will tell us that the V key has been pressed, for example. So there's quite a lot of things to do if you're reading more than one key. It does mean that some of the times you can detect multiple key presses at once. That works if they are fitting on the appropriate parts of the matrix. Other times you have to make multiple calls. An easier way of representing this might be this table, or it might not. It all works on how you conceptualize the keyboard matrix. What is your mental model for how that matrix works? And sometimes this is easier, sometimes picturing it as an actual matrix is easier. But there we have that. That's an example of how the keyboard works. Now we're on to graphics. And this is where it gets properly more fun. And it's also where I wish this was not water. I also saw that someone had written something in the chat. Unfortunately, I can't actually see the chat on my screen because I've got other software running. So excuse me if I'm not responding to what you said. Oh, similar to using the pipe. Yes, I believe I have seen that. Excellent. There we go. So graphics. Everyone ready for this? Right, deep breath. So I'm only going to talk about standard mode graphics here. I'm mentioning that because if there are Spectrum fans, they will know there are other modes Spectrum can be coaxed into. Not interested in that for now. I'm only going to do the standard mode, which is 256 pixels by 192 pixels. That's not a bad resolution, even for that day. That's okay, that's passable. It also had 15 colors. Now, the whole thing about power 2 says that should be 16, shouldn't it, Steve? No, it shouldn't. That is 15. And we'll come to the reason why later on. So, and oh, but you can't do it all. So you've got 256 by 192 pixels. You've got 15 colors, but you can't use all of them at the same time. What? Who built this? What, how, what? Hey, no. Okay, let's rewind. Let's see what's going on here. What on earth is this all about? So we have 256 by 192 pixels. That is true. The example image on the right is just one I happened to rip off Google earlier today. That image is 256 by 192 pixels. Now, when you're typing in code, you will see that as 32 by 24 8 by 8 pixel blocks. 32 times 8 is 256, and 24 times 8 is 192. So that's kind of fairly obvious. And they live at memory location hex 4000, which has a length of 6,144 bytes. But that's just bits, that's on and off. That is your 256.192 pixel map. So there's got to be something more here. So what's going on? Well, that's what's going on. This is the first part of an image being loaded. And with that in mind, I'm going to pause this and hope that I can come back to it later. Stop, no, spoiler alert. If I end this, I should be able to go to my browser, which has a video. I've turned the mute off because I'm pretty sure we don't want to hear the Spectrum loading noises. We know what that sounds like. Thoroughly horrible. This loading screen is going to be loading those 6,144 bytes, all of those sequentially. It's going to start at the first byte and go on to the second and the third and the fourth and so forth. So you will see the picture being built up using sequential memory locations. Just keep thinking of that as we load, using sequential memory locations. Watch the bitmap appear. Oh, and we do actually have some color, look, isn't that nice? So what is going on there? Right, so when this loads, these sequential memory locations start at the top as you'd expect. They go across, but then they jump down 8 lines and go across again. Then they jump down 8 more lines, then 8 more, then 8 more, then 8 more. Then they stop a third of the way down the screen and go back up to the top and do the second line. And then the second line of each of those 8 by 8 blocks is done all the way down. And when it's finished that first third, it goes on to the second third. Again, doing one line, jumping down 8 lines, doing another line, jumping down 8 lines, doing another one until it gets a third of the way down again. And it goes back to the top. And then it repeats. And this is like crazy. Why? Well, that's just the way it was designed. Don't ask me why. I need to get some proper first-hand acknowledgement on this. It's just a hardware thing. So if you want to draw a thing at XY, you get the Y coordinate and you do this calculation on it. You work out, the column numbers, which is that sort of 0 to 31, thinking of it in 8 blocks, 8 by 8 blocks. The line number going down again in 8 by 8 blocks, and then the pixel row in each line, 0 to 7. As we say, it's an 8 by 8 thing. And then by using those numbers, all we then need to do is take the pixel row value, bit shift it to the left by 8 pixels, or that with the line number, but only 3 bits of that line number. We take the other 2 bits of the line number and put them over here. We then OR it with the column number, which we stick down the bottom. Yeah. You know what I said about the audio taking 20 instructions to compute the numbers for 1 beep? And that was too much processing power. If you have to do this for every single pixel you plot, that is also too much processing power. So what do? Exactly the same thing. we pre-compute a table at the start of our game. We say, well, here are the 192 lines. I'm going to store the memory location of all of these lines. And then I just have to do a very simple fit shift pattern and a mask in order to determine each pixel. I can then optimize my draw routines that just say, right, well, we're starting on line 27. I'm drawing 27, 28, 29, 30, and just pull these memory offsets out of memory directly. There's a couple of extra pieces of code there that handle the time where you jump over a boundary. So if you were going 4, 5, 6, 7, then you jump to 8, 9, 10, then those are two separate groups of 8 by 8 pixels. So you need this set and then that set and some extra gubbins for that. But it's painful, but it's all a solved problem. It's not like this is new. And I was able to find some nice code that I could then appropriate into my own drawing routines so that I didn't have to worry about this set of calculations. Don't worry about the second part. We'll get to that later. We can now move on to color, I think. Here are the 15 colors. As you can see, each color looks similar to the one on the left, or you might say each color looks similar to the one on the right. That's because each of our colors is stored in 3 bits with an additional bit. So we've already said that we've got this 256 by 192 pixel block, but we don't have the colors for each individual pixel. What we have instead is an attribute memory block. Now this memory block is only 32 by 24 in size. Those numbers are familiar. Those are the 8 by 8 pixel blocks that we talked about earlier, each character being 8 by 8 pixels, and each one sits next to each other. No true type fonts here. It's fixed monospaced font. So every character in that 8 by 8 block can have an attribute. It has one attribute, and that attribute contains the color, and it contains flash, what is this flashing on and off, and it contains the brightness. Now the trick is here is that we've only got 3 bits for the color. We only need 3 bits. That's 8 possibilities. But what we have is we have 2 3-bit colors. We have an ink color and we have a paper color. So the ink color is whatever would a 1-bit be, for example, or a white bit be, an off bit, and we have paper for whatever the background would be. And in this way, every square can have 2 colors. Anyone that's ahead of me will know about the color clash problem. That's probably been documented well enough that I don't need to go into it. But suffice to say, if you have a background in red and your character is coming from one attribute bit to the next attribute bit, then at some point that color is going to end up changing and those colors will clash. Also, I mentioned the brightness flag. That's just one flag for both bits, which is why we have a bright version of the color and a less bright version. And funnily enough, a bright version of black is still black. So 15 colors rather than the 16. I believe the same is true of the color chips on the Acorn machines. So from that, we'll move on to how that's stored attribute-wise. It's not that interesting other than to say you can see the 3 pixels there for the ink color, the 3 pixels for the paper color, the brightness flag, and then the flashing on and off, which the system would do automatically. It would just go through and would just alternate the colors. And it is stored at memory location 5800 hex and in only 768 bytes. I mentioned earlier, don't look at the second part of that. Well, this is the attributes structure. You see, this is actually quite sane compared to the other layout, which is about how it used page modes. So, you've got third of the page, second third of the page, and so on. So why do it that way? Well, it saves memory essentially. So let's look at the memory. We had our pixel data at the first chunk of memory, that's 6,144 bytes, and we've got our attribute data, which has all the color information, in just 768 bytes. Whereas if each pixel could be individually addressed with its own color, would require 32K. Now, when your computer is only 48K, that's a significant chunk. So the designers had the good sense to say, well, we can't really afford all that space, so let's not use it. Let's, and then game developers ultimately found ways around it. Well, a lot of games, certainly on sort of 84, 85 era spectrum, their main character would be black and white, or at least monochrome in some way. Not because they were lazy artists, but by having the main character as monochrome, then there wouldn't be an additional color to clash when it moved across between the different attribute squares, which sort of come in handy. If you look at Commodore 64 games, yes, they have a lot more colors and they have a lot more individual control, and they do have a lot more memory, but half their memory is taken up with the graphics display. And because you can individually address each color, but with its own pixel, each individual pixel with its own color, you need more memory to store the graphics data. This is not just the data as it's being drawn on screen, the screen memory. The data that needs to get stored for each of the animations is much larger. So you lose out again. Whereas on the Spectrum, you just need the bitmap and 1 byte for the flag. So you save memory there as well. So I suppose I should probably talk a little bit about the game. I said I was more focused on the writing of the game rather than the engine, but I know for a lot of people, building a game is, just another thing. So building the game is just like drawing an owl. You've probably seen the meme. The first step is to draw the circle for the owl's body, and then you draw the rest of the owl. And it really is that simple. My approach to game development may be slightly different to others because of my history, but I'll run through it anyway, and then I'll show you briefly some of the games running in emulators. So the first step I build is the control system. That might seem strange when there's nothing else to do, but it allows me to come up with the key mappings, find the keys I like, allow the character to move with the keys. Are they moving smooth enough? Are they moving fast enough? Does the animation seem to work? If the character has got legs that run, does it look like they're running on a travelator, or are they sliding on the screen? So just making sure the character fits the world. And your control system is the only way the human has to interact with the game. So it better be good. You can build a most fantastic game, but if your control system just doesn't work, it's not satisfying. So I always start there and then build the rest of the world around that character and around the control system that the player has. From then I go on and build the environments. So if I'm satisfied that the player is running at a nice speed, if it feels right for the character in that particular game, they jump the height that you'd expect them to jump, then I build all the environment around that. If I find the environments are too big, then I make the environment smaller rather than make the character run faster. For me, that's an important difference. I think it was once calculated that in, I think it was Doom or Quake, if you were actually moving at the speed that it looks like you're moving in game, you would be running, physically running as a human at 30 miles an hour. That's obviously not realistic, but it makes for a good game. And they built it around that same principles. Let's make the control system feel good, but then worry about the environments and everything else later. From there, I move on to the enemies. I've got my player character running around now. So let's have some characters, some dragons, let them move. Are they moving fast enough? Are they moving slow enough? Can I catch them if I need to catch them? If I need to shoot them, can I reasonably shoot them, or do they move too fast for that? Do I need to speed up my bullets? What is going on there? Make sure that it's satisfying to attack the enemies. Then I look at the objects, which are the sort of, just the collectibles really. How many points do I award each one? Do I have a sound when I collect them? Do they animate to show that they've been collected? What happens there? And then from there, it's just everything else. Title screens, win-lose screens, animations, all the niceties. And essentially, this bit is the polish. And the polish for me is always that important part of the game, because it's what it shows that you as the developer have put a little bit of love and care and attention into the game, and I haven't just shoveled it out, even though that's essentially what you often end up doing sometimes. And then, once you've got a full game, you can just keep adding levels until someone tells you to ship it. So what's the collateral? Well, tell you what, let's pause on the collateral and let's actually show you some games. I'll show you the ZX Spectrum version first. I've loaded this into Matt's emulator. I'll start the game off. This is the most recent version of the game, I think. Yep, this is the most recent version. This is not the version that was on the Sinclair Vega. This is the version that will be out at some point in the future. And you move around. Yes, I know it's going slow. That's my machine and the fact I'm running a lot of stuff. You can see the character sort of animating. You can see the thing flash as I pick up an object. Let's go down, animate again. Another reason, again, for picking the whole, this is something that mimics what would have been written in 1982, is because in 1982, what would have probably happened, that's a little dragon that will kill me, is, and you can see, there you go, I've purposely left that final attribute there so you can see the color clash. I reasoned that if a game was being written in 1982, it would probably be a copy of another game, and that game would probably be one from the ZX81. So I figured, okay, in my mind's eye, what would a ZX81 version of this game look like? I then imagined how would they manipulate that ZX81 game to be a Spectrum game, to add something more to it. So I figured they would put the least amount of work in necessary, and this is what I came up with, to be true to the era rather than my own laziness. So that's that sort of thing. I won't bother playing through the whole thing. It takes a little while. Let's pause that. Let's close it down. And let's run up the ZX81 emulator. This is my one, oops, because it works in that, although I can't run it up. There we go. This is one of the things I mentioned earlier. There was no way I was going to program all of that graphic data in by hand with hex codes. So I wrote a 10-line piece of JavaScript that loaded an image and then output that into my assembler directly. And as you see, it's got a little scroll, it's got some instructions, and it looks incredibly similar. Bear in mind, I wrote this after I wrote the Spectrum version. I had to simulate in my mind what I thought this would look like. And then when I had some time earlier last year, because I don't know what happened last year, but basically I had a lot of time on my hands, a lot of time indoors, and not a lot of time at the pub. So I decided I'd do the ZX81 version. As you can see, I decided I'd have to scroll. I made things move faster because it's the ZX81 and it was never really a fast machine. So I figured, let's make things go a bit quicker, introduce some animations, and other clever, fun things. And as I said earlier, I then went back to the Spectrum version and added all these nice things, the animations, the scroll graphic, all of them added back in, pardon me, to the Spectrum version. So there we have it. And the comment I can see reminds me of Hack or Rogue on the VT terminals. Yep. Warren borrowed ideas from other games the same way that I borrowed ideas from his. Although the reality is, when I was writing this, I wasn't looking to improve on his game per se. I was just looking, essentially, if anything, I was looking for ways to make that game easier to code, that is. So I removed some things and improved the game by adding more objects. So he had one dragon, I'd have 6. He had one $1 prize thing, I'd have 10, that sort of thing. A very cheap and easy way. So those are our graphics. Let's get back to where we were. So we've now seen the game and how it gets built. It really is on a go slow tonight, isn't it? I don't know what I've done to annoy it. So yes, collateral. Once all this has been written, then what do we need to do? Well, I license it under GPL 3. That should also possibly be the AGPL library as well. My reasoning for this is I don't want someone to turn this into a ZX Adventure as a service product. This is kind of just a matter of course for me now. I've seen so many good open source projects that have been taken in-house and then closed off by someone selling it back to open source developers as a service. And while they're perfectly allowed to do it under GPL2, it's not what I want to happen to my software. I'm providing this software for people to learn from, to appreciate, and to then build upon. If someone then takes it and hides it away as a service, they don't get to do that. So I try and make sure all of my software is provided in a way that is always going to be open. And if someone does want to turn it into an as a service thing, then they have to come back to me and get an alternate license, which I think is more than fair. Next, I figured, well, it'd be nice to get a publisher. I'd got a publisher already with the ZX Vega. They'd put it onto their machine and built it into the silicon. I figured, well, it'd be nice to do that as an actual boxed product, a cassette. So, and I looked around at some of the publishers who still make and produce cassettes. And I wrote to one of them and says, well, I've got this Spectrum version. I know it's already been out, but if you're on a title, you're welcome to have it, put it out there. And to sweeten the deal, I said, if you want it, I'll tell you what, I'll do a ZX81 version as well, not realizing how long it was going to take me to do. So I did a ZX81 version, and we were going to have a cassette with ZX81 on one side and Spectrum on the other. What we ended up doing was doing the ZX81 as a one-off, as a special version, and then the Spectrum version came later with all the new ZX81 features due to be released next month or sometime soon. And getting a publisher was fairly painless because there's no money in these things. So there's no big fanciful contracts, because at the end of the day, no one wants to spend 200 quid on a lawyer fee for a game that is only going to be 6 quid and only going to sell 100 copies. It's just not financially viable. So finding people to do this stuff is comparatively easy, and publisher Simon is a nice enough chap anyway, so it's all good, and it's been reasonably well received considering. Need a cover? There is no way I can draw that. You've already seen the quality of my art. It looks like that. So a cover is needed. Again, that's publisher's responsibility, as is all the layout, getting things printed. The next thing you need to do is the synopsis and instructions. And you see it's a cassette inlay. It has instructions. I had to write them. Now, to me, that's a fairly dull thing. I mean, I've written books before. I don't object to writing 300 words for an inlay. But for me, it's just a case of the character goes around, you collect stuff, you kill stuff, end of game. But because I wrote it, I know what things you can collect, what things you can't collect. I know the keys. So you have to write something which is essentially very boring prose, but make it sound exciting and interesting. So I had to sit down and spend more hours than you'd think writing the blurb. So that's the synopsis for the game at the top, and then the history. I wrote a little extra piece in there for people who are interested about how it started, which is mostly what I've said here about started Spectrum version on the Vega, then got ported back. And that's it. Voila, all done. That's the thing that we've previously seen. As you say, you can toddle to Chronosoft if you want to pay it a visit. So what can we do in conclusion? Well, cross-development needs a good emulator, or sometimes more. Anyone that's done more than half an hour of development knows that you spend more time in your debugger than you do anywhere else. So you better have a good debugger, which in this case means a good debugger on the emulator. And if one emulator doesn't support it, then just go to another emulator. There's enough of them out there. And with a lot of them being open source, if the debugger doesn't have the precise thing you need, it isn't a massive job for you to add something very specific to your game or your particular bug. This is what I was doing with the JavaScript emulator on my EMF platform. I was writing very specific things in when I had an issue, and that helped the turnaround time immensely. Start small. As I mentioned, you can build every game with just these 3 components: draw a dot, read some input, make a sound. Start small, then grow. Build it up piece by piece. I also have a sort of a ship any day mentality for a lot of work that I do, which is to say, it's very agile in its approach, which is to say, oh, I build the thing that I need, and I build it well. I build it as well as I can, and then I add a bit to the end. Because if someone comes along and says, yeah, we've got to ship this now, or I get bored with it and I don't want to continue working, at least everything I've built works, is bug-free, and is a good piece of code. Even if it's not a bigger game as I could write, it is at least a quality game with what I have. And then the only criticism is, well, it was a bit small, isn't it? It's like, well, if that's the only criticism I get, that's not bad. I'll take that. And I also attempted to spend more time on the game than the engine, which ultimately I kind of did. The time when I didn't was when I ported it back to the ZX81. On the Spectrum, I was using the IX and the IY registers of the Z80 processor as index registers. The I in IX kind of gives you that clue. That's what it's there for. It means you can set the IX register here. You can say read a value from IX plus 2, IX plus 4, and that will get you X and Y coordinate out. And you say, well, give me IX plus 6, and it will get you your animation character out. That's very quick. That's very efficient. Unfortunately, if you do that on the ZX81, you lose your screen display, because the ZX81 uses IX and IY for its own personal use. And one of the things the ZX81 uses it for is handling the screen display. At which point, your screen goes all funny, you can't see what you're doing, and your computer has essentially crashed. So I had to go back and rewrite the whole of my engine and not use IX registers, but use HL and DE and BC instead in weird and wonderful combinations. It didn't make it that much slower, fortunately, but it was a rather thankless task, particularly as you can't actually run it. You can't just compile the ZX Spectrum version with its IX registers, because as soon as it hits one function that uses IX, your screen display goes. So you are literally starting from scratch. You're saying, I need to get one routine working without IX, and then I move on to the next one, rewrite it. So it almost feels like starting again. But I'd promised the game, and it's a ZX81. It's my first computer, so I felt I owed it to the industry to do that. So that's everything that's been planned, including some snafus that were not planned. But with that, I shall stop, take yet another breather, and invite questions.
Oh, thanks very much, Steve. I'll just stop the recording, and yeah, and people can have at it.